one is we're going to look at op amp as an inverting adder, as a summer. That is how it can add. That is in terms of addition. Are we there? Yes. Good. Op amp as what? As adder. So what we're going to do now is we will now. So this is IR, R1, R2. This will be I2, I1, V1, V2. And this is the diagram for op amp as an inverting adder. Adder now. In brackets, summer. That is addition. Okay? So we're going to the next one. Here, we're also going to apply the principle of virtual ground. So by the concept of virtual ground, what we're going to have is VA minus VB equals to 0, where VA equals to 0 and VB equals to 0, with a high input impedance Z in tends to infinity. Therefore, I1 equals to 0. Now we're going to apply the equation using the Kirchhoff current law now. Look at the current that's entering I1, I2. I1 is leaving. Okay, since we're having I1 here and I1 here, we may tend to use IR1, then IR1, 2, so that we have a difference. So, but in summary, let IR equals to IR1 plus IR2. Let IR equals to sum of IR1 and IR2. When that happens, we can say now IR equals to IF. And from here we can say, from this side with this, you can say this is IR1 plus IR2 equals to I what? F. So how can we get the voltage, the equation for the IR1? IR1 will be V1 minus what? VA. That is V1 minus VA all over what? R1 over R1 plus IR2 is going to be V2 minus VA by R2 IF, that is VA by V naught. No, VA minus V naught all over RF. That is the relationship that we hold here. Anybody, any confusion? No. Huh? No, sir. Okay. So when that is done, note that, you have to note that, already we have been discussing this, you have to note that VA equals 0 according to the concept of virtual ground, right? Please, you can come in. According to the concept of virtual ground, VA equals to what? 0. This will give you V1 minus 0 over R1 plus V2 minus 0 over R2 equals to what? 0 minus V naught by RF. This gives you V1 over R1 plus V2 by R2 equals to minus V naught over RF. For you to determine the output voltage of this adder or the summer, you first of all multiply top of the equations by RF. And this will tend to be V1 times RF over R1 plus V2 times RF over R2 minus V0 times RF over what? RF. This will simply cancel out at this level, leaving you with what? V1 RF over what? R1 plus V2 times RF over R2 equals to minus V0. Agreed?
Yeah.
Good. When that is done, then there is something that is very important. We have to put aside the voltage gains of this equation. This gives you V0 equals to minus, because this is an inverted output already with a minus sign indicating here. Okay? Then you put the braces. You have RF all over R1 V1 plus RF all over R2 dot V2. This is it. Now at this level you have this equation, but whereby if this is the output equation indeed, but if RF equals to R1 equals to R2 equals to 1, what are you going to have here? It will tend to equals to V1 plus V2 and then a minus. And this will give you the actual output of the inverting this thing. This one is the summer, and this one is giving you the actual sum of the voltages. Agreed? Op-amp as an integrator. The diagram looks same, but it's a little bit different. Can I create the diagram too?
Yes, sir. Yes.
Now, op-amp this op-amp as an integrator. This is the diagram. We are also using the same concepts, but a little bit different because we have a reactance here, which is a couple. Now, when current passes, current IC passes through capacitor C, we have IC equals to C dV over dt. Because we have, you think I have to change the time at that moment. Therefore, okay, let me finish this one. Maybe we'll go for 10 minutes. Come back, then we'll finish. By the concept of virtual ground, VA minus VB equals 0 and VA equals to 0, VB equals to 0, with Z to infinity equals to infinity, then I1 equals to 0. What's the problem? What's the reason? Therefore, the currents we have here, IR1 and IC, right? IR1 equals to IC. So what is IR1? That is V in minus VA all over R1 equals to what? Equals to C D all over dt. So the V here the V here could be the V differential, which is equals to C D bracket V1 VA minus V out all over what? dt. VA minus V out. That is to get the current that's passing through the capacitor. When it was a resistor, it was VA minus V naught, is it not?
Yes.
That's what we're doing now. So that gives you VA minus 0 over R1 equals to C dV C D bracket 0 minus V naught all over the what? T. This gives V in over R1 equals to C D minus V naught all over the T. The reason why you're having a minus here is because of this. 0 minus V naught will give you minus V naught. And we cannot allow the minus to be inside, how to bring a little bit outside, okay?
Yes.
Thus informing you that it is an inverting output, right?
Yes.
Good. So when we have that, what we're going to do is integrate both sides of the equation. If you integrate both sides of the equation, first, but before you integrate both sides of the equation, there's something that you need to do. Let me hold on first. There's something that you need to do. You have V in all over R1 C minus equals to D naught all over dt. This is the time you can differentiate both sides of the equation now. So first, let us arrange first before we do that. Equals to minus V in all over what? R1 C. So therefore, integrate both sides of the equation. When I say both sides of the equation, I mean here and here, right?
Yes.
Okay. When you do that, you are going to have here as V naught equals to minus 1 all over R1 C. You cannot integrate this constant, right? This is the sign of integration, right? V in T with respect to T from 0 to T. This is the solution for the something, because this one will definitely move to this place and this is what we're going to have. Okay? So we have just a few pages to finish this. It's not much again. The other one is just the evaluation. So if we are going for break, I think we'll have just 3 pages to round up. So maybe if there's going to be any break for them now, it should be done. We'll last a little bit, 10 minutes, and then continue finishing. Actually, yes. So how do my boys and my daughters here? So the diagram looks like, I'm not going to clean this one now because I want us to be sharing something that is very important. Okay?
Yes.
You know, this is a new marker that is behaving like this. Well, this marker is not too good. I have to avoid it. It looks like permanent marker somehow. I'm going to use it to defuse the board. Okay. This is the diagram we have, and already I've shown you the equation that's derived when current passes through a capacitor, right? Which is IC CdV dt, right? Now, and we have been discussing about the concept of virtual ground here. These are the key things and the effect of high input impedance to the input current to the differentiator. And I made mention that let me use the red again. That is when, I'm not giving the title. Op amp as a differentiator. So when you have this, you look at the position of the capacitor for integration, and then the position in which the capacitor is connected for the differentiator. You can see just a swap, okay? Just a swap. And though it has a very large effect on the diagram here. And with this, we can also follow all the scientific laws that are required for us to concept of virtual ground. VA minus VB equals to 0 implies VA equals to 0 and VB equals to 0. When Z equals to infinity, I1 equals to 0. When the input dependence tends to infinity or as at infinity, the current at the input of the op amp at the inverting input is equals to 0. I don't need to write it later this thing because we have been discussing it. So for this reason, you can see that we're going to have a question for IC equals to what? Equals to what? IF. We're going to have question for IC and IF. So if the equation for the IC here is going to be d C dV the all over what? dt equals to what? Equals to what? Equals to what? Equals to what? IF will be what? VA minus V naught, right? Yes. VA minus V naught all over RF. Now, but VA equals to 0. Therefore, CD V in minus VA all over what? All over what? dt equals to what? VA minus V naught all over what? RF. You know that VA here will be affected because since the current is flowing this side, we are going to start taking the voltage from here, VE minus VA. But if the current is flowing this way, it will be VA minus VE. I have to know the direction of current when we are doing this kind of equations, okay? The direction of current determines the direction in which the equation will be flowing. So, in this case, we are going to have CD bracket VA minus 0 all over dt equals to 0 minus V naught all over RF. And with this, we will have it as CD V in by dt equals to minus V naught by what? RF. If you have this kind of relationship existing, first of all, we would like to look at something that is very, very fundamental here. If I said DC dV in all over dt, okay, equals to minus V naught all over RFC, CRF. Maybe this one goes to the other side. Will I be wrong or right? So if you want to get the output of this equation properly, what will happen is that this very equation will have to cross multiply itself for you to have the V naught. Or you have to multiply both sides by CRF. This will be GV in all over dt bracket CRF RF. You know, S with a subscript is not as big as the R. Are you seeing it? Yes. Equals to minus V naught all over CRF times CRF. This will now gently cancel out, giving you the minus V naught. And why this is in this manner, you have to ensure that you bring out the terms in such a way that the equation will look very standard. This will give you this will give you minus RFC. The C is bigger, please. D all over dt V in it equals to V naught. In essence, this is exactly what you are expected to get as the equation of this very figure here, op amp as a differentiator. This is what I expected to get. This is how the output equation will look like. So, looking for me? Huh? I think it's inside. Yes, it's there. Now, we're moving to the next one, op amp as a non-inverting amplifier. We'll be looking at inverting and inverting. We have discussed the integrator, we have discussed the differentiator as an amplifier, right? Now we'll look at the non-inverting. All the other ones we've been discussing are inverting. This is non-inverting we're going to discuss. So, very soon, just have a little pattern. We'll roll up of here. Then you see how the equation will begin to change the phase. For the non-inverting, the direction of current one changes. For the non-inverting, below shows the circuit diagram of a non-inverting amplifier. So for a non-inverting, you are going to have something like this. Yeah. This is negative, positive, 0. And some of you will be asking, but you are still connecting on that, on the negative now. I think you are asking that question, huh? Yes, sir. This is 0 volts, and this is what? R1. And the direction of current here. The direction of current here is I what? I R1. This R1 now. Are you see the direction of current? Yes. It's not going this side, it's coming backwards because it's a non-inverting component. And for this, it is connected in a non-inverting mode. So now, this is what you have. The current here is also flowing this side. But here, the current tends to enter. Right? This is RF, and this is I what? F. And here, also, another supply. This one initially was going to ground. Yes. Was it not connected to ground? It's connected to the ground, but now it's no longer going permanently to the ground, and there's another supply at the terminal B. Here is a zero potential level, and here is VB, and this is what? VA, and this is V into. And then, when we have this kind of thing, the reason why
you said you did the last part, and your explanation, it is no longer connected to the earth. Is that what you say?
No, for the other ones, the VB was connected to earth. There was no supply.
That was a supply.
There's a supply here now. Here, there's no supply.
But still carry the sign of earth.
Sign of earth. No. Is there any supply that does not go to the neutral or to the general earth?
It is.
Because any supply does not go to the neutral or the general earth, there's no way it can flow. So here, what we're having here, by the concept here, this is a figure, let me write the figure, non-inverting amplifier. Use just generally for non-inverting amplifiers, okay? Yes, sir. Are you getting me?
Yes, sir.
Now, if you want to carry out the analysis of this very diagram here that you are seeing, one, note that there's a supply here. There's a supply here. So, if there's a supply, VB is not connected to the general ground. VB is not connected to the general ground where you have 0. Here, VB was going to ground direct, so here it was 0. Are you hearing me?
Yes.
But here, the supply to VB is determined by V in. It's determined by what? V in. So there's no way it will be 0. So we are going to have something by the concept of virtual ground. VA minus VB equals to 0. But since VB is not connected to the ground, but is connected to V in, then VA equals to VB equals to V in this relationship. Are we together?
Yes, sir.
But because the impedance of this op amp is very high, almost at infinity, however, as Z equals to infinity, I1 equals to 0, that condition still stands. That condition still stands. And looking at that, now we can determine the current that is in this circuit. Actually, if you look at it, the current that is coming in is IF. It is being distributed at IR1 and VA at this level. Okay? Yes. So what will happen is that we are going to get the equation of IR1 and then IF. Are we in tune? Yes. Good. This is now, hence, IRF equals to, hence, IR1 equals to IRF. What are we going to have here as our IR1? This will be V. This one is going to 0. This one is going to 0. It's going to 0. Something is... Okay. No, nothing is connected here. Sorry. I thought something. If something is connected there, I can still derive the equation. Because that one would have been V in, subtracting this. But since nothing is connected at this level, based on this diagram, what we're going to do is that we'll now say VA. We'll have nothing that will affect this other one here. So it will be, instead of having VA, because of the direction of current, had it been something is connected here as V in. Are you getting me? Yes. Maybe this would have been V1 and V2. The equation here would have been VA minus V in all over R1. But since nothing is connected here, it will be VA minus 0. It will be VA minus what? 0. Because there's no supply connected at that point. So now, we are going to have VA minus 0 over R1 equals to, here will be V0 minus, because of direction of current, it will not be VA to V0. It will be V out over the V at this junction here. And that will be what? V0 minus VA over what? RF. I believe you are following based on direction of current as I was explaining. Yes. Okay. Okay, this is good. So when you have this, and mind you, we said V in equals to what? VA equals to what? V in based on what we were saying. So if that is the case, what are we going to do here? we would have said from equation this, VA equals to V in. Why VA, right? VA will be what? Since VA equals to V in, equation this becomes what? V in minus 0 all over R1 equals to V naught minus V in all over what? RF. I think we're making progress.
Yes.
So, now, what we're going to do is we say V in over R1 equals to V naught all over RF minus V in all over RF. So bring the V in and the V in RF together so that you have a common V in. Okay? If you arrange what you are going to have that will be V in over R1 plus V in over RF equals to V0 all by RF. Because this one will have to turn and cross the equal sign and become positive. Abi? Yes. So if you have this relationship, what is expected of you to have at this juncture is V naught or RF equals to V in bracket 1 over R1 plus 1 over RF. Are we there? So if you have something like this and you decide that you want to eliminate the RF, how are you going to eliminate it? We can even come back to this equation and eliminate the RF by saying V in over R1 times RF plus, for those that may not understand, V in times RF all over what? RF equals to V naught over RF times RF over 1. You know that this one will gently cancel out. Okay? Leaving you with these other components here. And another thing that will happen is this one too will cancel out. Abi? You have V in RF over R1 plus V in equals to what? V naught. So automatically, if you remove the V in here, you are going to have your answer as V naught, or you have RF over R1 plus 1. Or how do you do it? Because if you remove the V in here, the V in here will not be, because you have to make it independent in this case, and it will be V naught at this level. Can you see? You can rearrange. By this, if you rearrange, you are going to have the equation as V naught equals to 1 plus RF over R1 by V in. If you look at the inverting, something was RF by R1. That is, the overall gain was what? RF or R1. But the non-inverting is 1 plus RF by R1. If you check, those of you can be writing, you will notice that what I have written is true. So this is how you can determine the equation of an op-amp connected in a non-inverting mode. Another diagram that we need to op-amp as a voltage what? Follower. Here you have, this is the output, right? This is connected directly to no component, and this one comes down to the supply. This is VB, and this is what? VA. Are you getting me? And here is V in. So, for the voltage follower, the output, the input is exactly what you get at the output. It asks, yeah, it's exactly what you get at the output. So in this case, we can see that VB equals to V in. There's no magic. That one you know that it's V in that is supplying VB. So if 2 amp is flowing here, it's the same 2 amp that will go to that VB, is it not?
Yes, sir.
Okay. The node B is maintained at the potential of VB. The node VB, the node B, you can just say the node B is maintained at the potential of VE such that VB equals to V in. That is, what is here is what is flowing into VB. Yes. So it is the same. It is the same. By the concept of visual ground, you know that VA equals to VA minus VB equals to 0. That is by the concept of visual ground in this case. Then the node A is directly at node A, let's say A, and this one B. At node A is maintained at node A the potential of VA is equal to V naught. That is VA equals to V naught. That is what is flowing here is exactly what you are going to have at your output. Can you see how the arrangement looks like? Yes. So, since the output voltage is equal to the input voltage, that is what is obtained concerning the voltage follower. This is the diagram for op-amp as a voltage follower. As a voltage follower. So that is it. As a voltage follower, whatever is coming at the non-inverting input is exactly what is getting to that terminal. And what is coming at the inverting input is exactly what is going to the output. Okay? You don't have any long. You cannot go and fabricate anything. I have just, you can just have 3 minutes to finish up now.
Yes, sir.
So now, this is one for voltage follower. Now, op-amp as a comparator. Op-amp as a comparator. Good. So op-amp as a comparator, in this case, we have a diagram that looks like this. This is negative, positive, right? Yes. We have your V in here, and then here we have something. We have a reference voltage. This is V reference voltage here. So if you have a reference voltage, do you know what I mean by reference voltage? Yes, sir. It's a voltage that wants the system to work with. Maybe I want the op-amp to be delivering 5 volts, like for microcontrollers or microprocessors. Yes, they take only 5 volts. So you use this kind of diagram to have a reference voltage of positive to 5 volts, but particularly 5 volts, so that anything that is swinging more than that, it should shut down. I think my point. Yes, so most of these things you see, they are designed with specific components, with specific component functions like that. Yes. So here you can see that a comparator is a circuit which compares a signal voltage applied at one of the outputs, one input of the op-amp with an unknown reference voltage at the other input. If you apply V in here, the V in will compare with the voltage that is here. Are you getting me? Yes. And I want to let you know that when the input voltage is less than the reference voltage, Vref, the output voltage is at maximum negative. Yes. If the voltage here is less than what you have here, the positive, you are going to have a negative output.
Sir. How is it possible, sir?
Huh?
How is it possible?
How is it possible?
Yes, sir.
No, hala. I'll discuss it. You see, as you can see this very something here. Maybe if you have a reference voltage of 2 volts. Okay?
Yes, sir.
Or let me put 5 volts. And then you give the V in here to be like this is 5, this one you can see 2 volts. Okay, that is 2 volts, right? 2 volts here. Just say 2 volts. It's less. Okay?
Yes, sir.
Minus 5 volts. You are going to have minus what? Minus 3 volts. And this thing will swing to maximum what? It will swing to what? Maximum negative. Maximum negative. So if you have like 7 volts, that which is higher than the voltage reference, 7 volts minus 5 volts will give you positive 2 volts. It will swing to maximum positive in this case. That's what I'm saying.
Yes, sir.
Are you there?
Yes, sir.
So now, but there is something you need to know. I told you that op amps do have a voltage limit. The voltage limit is the power supply. If the power supply is delivering 12 volts positive and 12 volts negative,
Yes, sir.
and you are having a voltage that is very close to or equal to the way cutoff. So you may have something about 10 volts maximum and 10 volts what? Minimum. So there's a diagram that you need to see to consider what I'm talking about. If, for instance, you have this type of diagram now, this is the reference voltage, right? This is V in, and then you have a supply of this type. That is with respect to what? Time. AC changes with time. This does not have change with time.
Yes, sir.
The time line is always what? 0. So it's obvious to ask you if a DC current is flowing, what is the time this thing? And you say it is 1 second or minus 1 second. You are getting 0. It does not have any time. It's only 0. Only 0. So now, if you have this type of thing, and you take this one as the Vref, as the voltage reference, Vref. Can you see the voltage reference is less than the V in?
Yes, sir.
Is it not? And this is here the 0, but it has shifted to a level as maybe you can say 5 volts here as the voltage reference. Then you decide to build the diagram for your waveform of your system. Then you have this one, something like this. Or should I put it inside? Okay. Now look at it very well. Here you have another one. This is 0. Here is V sat. That is V max. And then you have positive. And here negative V max. And that is minus V sat. Are you getting me? So when you have something like this, what do? What this diagram is telling you that when the Vref is at this point, the op amp operates. Between here and here, the op amp is off. And then at this point, here, between here and here, the op amp is what? Operating again. Between here and here, the op amp is completely what? Off. And then it starts rising again for another step. This is the way it works. So that is exactly what I expected to do. When Vref is set to 0, when the Vref here comes back to 0, what you are going to have is 0 crossing detection. You are going to have a 0 crossing detection. That is, there will be no single effect. If Vref comes back to 0, there will be 0 crossing detection. So that is it. Now, but the diagram you are seeing here is for the voltage output. This is V out and this is V in. Can you see? Another thing you need to let you know about digital electronics is that any system you power with a particular supply, there's a waveform attached to it. Are you getting me?
Yes, sir.
For instance, you have something like this. 0, I'm just giving you, I'll finish the lecture, I'm giving you a reference of something. 1, 1, 1, 1. If you want to get this number, or maybe 0 here, first of all, this is a binary, you want to change it to what? To decimal, right? Yes. Or you want to draw the waveform of this very number, this very figure you see on the board. In digital electronics, this one indicates a fall. Abi? This is 0. 1 is a rising. Another one is a rising. 1, 1. Then the 0 is a fall. And then the other one is a rising. That is how the waveform of this thing looks like. So there are times we give a very large figure and tell you to draw the waveform. Maybe about 3 of them. So after you have drawn about 3 or 4, somebody, okay, if I decide to write another one like this, I said this one is okay, this one is rising in the middle of these ones. Let me just show you something that you need to know about this electronic systems. In digital electronics, the output of this waveform, this W1, waveform 1 and waveform 2, if you want to draw the waveform of this output waveform of this something, you know what I'm going to have? This one is this 0 and 1. You are going to have a rise. This is 0, 0 and 1. You are going to have another rise. This is 0 and 1. You are going to have another rise. This is 0 and 1. You are going to have another rise. But let's take, for instance, it continues like this to this level. Then, where you have 0, maybe you have a 0 here, you have a 0. Then it will come here and drop and begin to rise because this is positive, positive. This is how they are drawn. This, you can do it by, first of all, trying to know, it's not just about changing binaries to decimal numbers to binary, hexadecimals and rest. Sometimes you will require to draw waveforms. This deeper aspect of it. And these are the kind of things that engineers or designers of computers use to determine outputs of what they want to do. So having studied this topic, we have successfully come to the end of operations of operational amplifiers. And what we are going to study tomorrow is another good topic, an exciting one, a topic that will make you to understand more about generally how systems work without being powered, or being powered and the battery is removed away, like your car. You power your car, you remove your battery, you can drive to any place until you switch it off. These are the kind of things called process.